this computer. Good. So we're recording now. October 30th, 2024. This is Physics 6. And we covered every section of chapter 5, and we're just skipping this one here, 5.7. This is a more difficult section, right? That's why it's have a star here. And we're going to start chapter 6, Work and Energy. Okay. Okay. And while we are at that, let's place it right here. Okay. This is insert page break. Now, today is October the 30th, 2024. Wednesday. We're done with chapter 5. We are done with chapter 5. And we are skipping 5.7. Vertical circular motion. Okay, we will start chapter 6. Chapter 6, work and energy. Okay. The concept or idea of work. Why do we study work, right? Why do we study work in physics? Oh, that's because it has reasons. It has a very important, it has very good reason. Okay, the concept of idea of work allow us to solve problems in an easier way, to solve physics problems in an easier way. As of now, we have been using the concept of force and force diagrams, right? And force diagram and free body diagrams, free body diagrams to solve problems. As of now, we have been using the concept of force and free body diagrams to solve problems. However, note that force is a vectorial quantity, which is more difficult to work with compared to scalar quantities. Okay? The concept of work, on the other hand, okay? On the other hand, the concept of work is a scalar one. On the other hand, work, okay, let's put it this way, is a scalar quantity. Is a scalar quantity. And it can be used to solve the same problems that we solve using the idea of force. Okay? So we have this interesting situation in which you can solve a problem using either vectorial quantities or scalar quantities, okay? That's why we introduce this concept of work to allow us to solve physics problems using scalar quantities, okay? And the idea of work, we start, we start by defining mathematically the concept of work. Then we expand it by defining a quantity that is closely related to work and you have already heard of the idea of energy, the concept of energy. Okay? And so let's start with our definition of work. So let's start with our mathematical definition of work. I want to caution you for several, but before doing that, I want to caution you about some definitions of work that we see in the literature, okay, in the physics literature, in the textbooks of physics, and even dictionaries, okay? Let me give you an example, okay? Let me give you an example. Let's go to the internet and let's see the definition of work is all about, okay? Definition of work in physics, right? Here you go. Measure of energy transfer that occurs from an object that occurs when an object is moved over a distance by an external force, at least part of which is applied in the direction of displacement, okay? So that's the definition that they give to in terms of work. The only problem of this definition is that now we have to define what energy is, okay? That's the problem. So let's go ahead and see what's the definition of energy in physics, right? You go. Look what funny thing they do to us, okay? They define work in terms of energy, and then you go find out what energy is. They define energy in terms of work. It's not helpful, right? It's just like a dog trying to catch his tail and people moving in circles, okay? That's how they define energy. They define energy in terms of work, okay? And work in terms of energy. And that's why I want to caution that, because now we should concentrate specifically on the mathematical definition of work. Okay, and the mathematical definition of work. Okay, mathematical definition of work involves the idea of force and displacement. Okay, and I'm going to show you here a drawing. Let's get this thing here. You go. see here. Okay, I guess we can stop writing here, copy everything that you have. Okay, and new and place right here. And I'm gonna save that as illustrations 07 -work. Okay, so here we go. And now I'm gonna play the movie for you. Okay, and the movie starts logically with the x-axis. Okay, here you go. Move it right in here. The next frame of my movie is going to be the y-axis. And the next frame of my movie, I'm gonna place a mass right here. And let's make it, the thing looks nicer by erasing the grid lines. Okay? X-axis, y-axis, mass, and then there's more. There's more. Remember that I told you that the concept of work involves a force, okay, and a displacement, right? So here you go. I'm going to apply a force to this object. And this force makes an angle, theta, with this object, with this with the horizontal, not with the object, but with the horizontal direction. Okay. As we apply this force, the object may or may not move. Okay. Let's say the object moves. Let's say the object moves, right? If the object do not move, that's because we must have another force countering this applied force, right? But if this force is strong enough to overcome another force in the opposite direction, the object will manage to move. Okay, so here you go. X-axis, y-axis, they cross, the two axes cross at the origin, the mass, force applied, this force makes an angle theta with the horizontal, and this force result in a displacement of the object, of the mass that we're dealing with. I need to illustrate all of that for you to understand the concept of work, okay? And this object moves a distance, let's say a distance d, right in here. A distance d, right here, right? So you need all of that stuff to understand what's gonna come next, right? Okay, so when you have a situation like that, the work that we say that the work done by this force is going to be given by the component of the force in the direction of displacement. Okay, the component of the force in the direction of displacement times the displacement. In this case, the component of the force in the direction of the displacement is going to be the force times cosine of theta times the displacement. Or, since we illustrated the displacement as being d, let's put d here as well. Okay, that's the definition of work. I want you to memorize the definition. Okay, memorize this definition. Okay, and let us now talk about the unit of work. Okay, work done by a given force F. Right? So we go ahead, use our notation for the units of a quantity, which involves the square bracket, right? Square bracket means the unit of whatever is inside the square bracket. So the unit of the work done by a given force is equal to the unit of force times the unit of displacement. Okay? The unit of force is newtons, the unit of displacement is meter in the SI system, and this combination that you see here appears so frequently in physics that we give it a name of joules, abbreviated by the letter J. Okay? That's the unit of work. And by the way, joules is also the unit of energy. If you look at your electric bill at the end of the month, you will notice that the bill charges you by the amount of electric energy used, right? Used. And the unit used by the utility company. Do you know what's the unit that we use for in the utility company? Anybody want to say something about that? If you're familiar with your electric bill, let's see here. Let's see if I can get an electric bill out there. Electric bills, right? Sample, electric bill sample, electric bill sample. Let's see here, sample electric bill. More another student coming in. Well, next time, if you have never paid attention to that, next time take a look at their electric bill. Okay? Let's see if this one is a good. No, they are denying me access to this one. Let's try this one here. Let's see this one here. No, they're denying me access to. What a shame. Is it? Huh? Strange. Okay, what about this one here? Do they let me in? Let's see. Yeah, okay, good. Look at the statement of this electric bill, right? Oklahoma Electric Cooperative. Let's see here, usage history. Okay. That's the amount of energy used by, let's see, this business. Is that a business? Looks like a business to me because a house wouldn't use that much of energy per month. Okay, it's a lot of energy. The regular house uses something I'm doing at least 300 kilowatt hour, and that's the unit that they use in the electric bill. Okay, kilowatt hour. This unit of kilowatt hour is related to the unit of joules. There's a relationship between this unit here and the unit of joules. Okay? So take a look here, 2039, 2083, and so on, right? 425. In the summer, they use very little for some reason. Okay? So that's the unit of energy that we use that's using the bill, in the electric bill. Okay? You will notice that if you look at your electric bill at the end of the month, you notice that the bill charges you by the amount of electric energy used, and the unit utility company is not the joules. It is instead the kilowatt hour, which, by the way, is related to the joules. There is a mathematical relation to the joules. In other words, there is a mathematical relation between kilowatt hour and joules. Okay? And that's going to be a nice exercise that we are going to do. How do you change from joules to kilowatt hour? How do you change from kilowatt hours to joules? Okay? So that's the definition of work that you have to have in mind right now. Okay? Now let's do a very simple example. Example one. We always do a very simple example. And then as our knowledge increases about this concept, we get into more and more difficult examples, right? So here you go. I'm going to illustrate this example. Example. I'm going to put it here. Example. Okay. So here you go. Look what we have here. We have this force of 1 Newton in the horizontal direction. Exactly. And this force, this 1 Newton force, yeah, I did something wrong here, right? Propels this object a distance of 1 meter. And then I'm going to ask you, what's going to be the work done by this force? Okay, what's the work done by this force? Okay, so here you go. This is a very, like I said, this is a very simple example that just applies straightforward formulas in a straightforward way. A force of 1 Newton along the x direction. A force of 1 Newton is applied to an object. This object, this place, and this object displaced 1 meter along this the x direction. Find the work done by this force. Okay. So this one is a very straightforward application, right, of formulas. Not this one right in here. Solution. And then we're going to go for a little bit more difficult problem. Here you go. Straightforward application of formulas here. There's nothing much to think about it. Is work fx delta x, f cosine of theta delta x. Theta in this specific case is going to be 0. The force is going to be 1 Newton, 0 degrees here, right? And the displacement is going to be 1 meter. Cosine of 0 is 1. Consequently, what we end up getting is 1 joule. Straightforward. Just one line to solve this problem, right? And then we have this other problem, a little bit more difficult. Why is it a little bit more difficult? It's a little bit more difficult because the force now is not parallel to the horizontal direction. It's not horizontal. The force is not horizontal. As if we have an illustration here. No, we don't have a new. Oh, yeah, here you go. We have an illustration here. Let me move this one right in here. Okay. Now the force in, just like before. Gotta fix that. Oh, here we go. like that. So now at this point in time, you may have already figured out how to do this problem, right? This example, not this problem, but this example. Angle theta now is 60 degrees. Cosine of theta of 60 degrees is going to be half. Consequently, we get half of a joule. Okay. And then, we can come up with another example. Okay. Remember that when I told you that the work done by a given force, right? The work done by a given force, I have to specify which force we are talking about. In these two specific examples, I specify this force F. But if I want, I can specify a different force. I can, for instance, specify the work done by the weight of the object. Okay, I can do something like that. Okay, and let's erase that. I can also say, come to you and ask, what's the work done by the normal? Why the object is placed 1 meter along the horizontal direction? Okay, I can also say that. So I can even come and say, what's the work done by a set of forces, by a summation of forces? I can do that as well. Okay, and it doesn't matter. The work done by a given force doesn't have to be a specific force. It can be any force, provided you specify which force this one is, right? And now we can go ahead and look at this special case here. What's the work done by the weight of the of during this displacement? What's the work done by this force here, by the weight during this displacement? And notice that the displacement is the horizontal direction and the force is in the vertical direction, right? So we go ahead and formulate this example. And the work done by the weight of a force. Okay, here you go. While an object displaces 1 meter along the horizontal direction. Okay, we have to find the angle between the displacement and the force. This angle is going to be 90 degrees, and cosine of 90 degrees is going to be 0. It doesn't matter if you know or do not know the m, the mass of the object, okay? We have the same thing for the normal force in this specific case, okay? Example 4, an object displaced 1 meter along a horizontal surface. What's the work done by the normal applied to this object, right? Just like the case of the work of the weight is 0. The work done by the normal is also 0, okay? The above examples are exclusively for the work done for a single, in the above examples, right? Here you go. In the above examples, we asked the work done by a single force. Okay? But we can also ask, what is the work done by a set of forces? Okay? Keep that in mind. And, now we're going to have this, example 5. Example 5 is one example of a set of forces. An object displaces 1 meter along a horizontal surface. Okay, what's the work done by horizontal surface? A force. What's the work done by the normal, by the weight, and the force applied to this object? What's the work done by the following set of forces? The normal, the weight, and the force F applied to this object, and a force F applied to this object. And by the way, this force F, in this case, this force F is along the x direction and is equal to 1 Newton, okay? So the way we solve this problem is by, I'm going to state here solution. What we are asking the work done by the normal, and I'm going to put the vectorial notation here. I'm going to put that in vectorial notation. The work done by the normal, the work done by the weight, and the work done by the force F, right? That's what we're asking. The work done by this set of forces is going to be what? The summation of all these forces okay? Summation of all these forces. And let's see here. I'm going to put a magnitude here. Magnitude of all these forces times the cosine of the angle of all those forces with respect to the times what? Delta x. Okay? We can also write in the following way. Let's see here. When I put cosine of theta here, I mean cosine of theta is the angle that the net force makes with this displacement, okay? That's what I mean here. So if I were to here write this equation, would be something like that, magnitude of the net force, right? Times cosine of the angle that the net force makes with the displacement. That's what theta net is all about. Another way of solving this problem is just to write my equation like that, work done by the normal force, okay, plus work done by the weight plus work done by the force F. And now I'm going to fix that. That would be another way of solving this problem. So you get the work done by each separate force and sum their work separately, okay? Because the normal force makes an angle of 90 degrees with the displacement, the work done by the normal is going to be 0. Here too, because the weight makes an angle of 90 degrees with the displacement, the work done by this force is going to be 0 as well, but not in the case of this force F, which is parallel to the displacement, right? And what we end up getting is 1 joule. Okay? So what? There is another example here that I'm gonna make for you, okay? What if a force is makes is in the opposite direction of the displacement? Okay. What if a force? Here you go. Para put that. What if a force in the is in the opposite direction of the displacement? Okay, like the force of friction, force force of kinetic friction, right? That's what this example is all about. So let's put it this way here. See example below. See example below. And I'm gonna go back here to my drawing. Let's see, we have a drawing here. This one we covered. Okay, so here you go. The object is displacing from the left to the right. And there is a frictional force along the way. This frictional force is opposite to the displacement. Okay. And what does it mean that the frictional force is opposite to the displacement? It means that the vector force is to the left and the vector displacement is to the right. Huh? Here you go. That's the vector displacement here. You want to put it in a different color. Okay? I'm going to put it as being vector, let's see, delta x. Like that. That would be my vector delta x. You gotta look at the angle that those two vectors make with each other, right? I'm gonna get my vector force, I'm gonna place it tail to tail with the other vector, and we're going to measure the angle that those two vectors make. In this case, the angle that they make is not gonna be 60 degrees, it's gonna be 180 degrees. Okay, 180 degrees. And I can't even pick up. Get, yeah. I'm gonna raise this one here. And this angle theta is going to be 180. I'm gonna make this one green. And then we can solve the problem. Okay? An object displaced 1 meter along a horizontal surface. What's the work done by the force of friction, the force of kinetic friction that is equal in magnitude to 1 Newton, right? And then the solution is going to be like that. Here I'm asking just the force of kinetic friction. I'm not asking the work done by a set of forces, okay? Here you go. The work done by the force of kinetic friction is going to be the magnitude of the force of kinetic friction, the cosine of the angle between the force and the displacement, okay? And delta x. This force here of kinetic friction is going to be 1 Newton. This cosine is going to be 180 degrees. Okay. And the displacement is going to be 1 meter. Right? Straightforward, right? So this cosine of 180 degrees is going to be what? -1. Okay? this one here already multiply the other one. And then what we get? We get that the work done by a given force can be negative as well. 1 minus 1 joules. Okay, can be negative as well. 6 different examples. Okay. That the force can be positive, can be zero, it can be negative. The work done by the force can be positive, negative, or can also be zero. Okay. We do not need that. Let me erase those two. Okay, and any force, so any force, that doesn't have to be the force of friction, okay? Any force contrary to the displacement will do negative work. Any force, not just the force of friction, not just the force of friction. Okay, will do negative work. Okay. Let's go here. Everything that you saw here, everything that you saw here are for constant forces. Okay? That you saw above. All examples that you saw above, okay? All the examples that you saw above are just for constant forces, are just for constant forces. What if a force changes with the displacement, okay? What if a force changes the displacement? There is a very important example. Let's see if I have an illustration here for you. One more student coming. Let's see. Yeah, unfortunately, I don't have an illustration here. Okay, let's see here. Well, consider, for instance, the force that a spring exerts. The force that a spring exerts in an object. Consider that. Okay, and I want to get an illustration of a spring applying a force. Oh yeah, right here, I have it here. Okay, let's play a little bit with this spring, okay? We're going to come up with some thought experiments. Okay, so here you go. I'm going to get all those. I'm not gonna use everything. Examples. Here it's gonna be examples. Examples, force, variable force, variable force. Okay. So here you go. One example of a variable force is the force that a spring applies over a mass. I attach this spring at a wall, for instance, and attach the other end of the spring to the mass. Okay? In this illustration here, the mass is initially at its equilibrium position. So the spring is not stretched, neither compressed. Can you picture that? Right? Try to picture that. When you compress the spring is gonna try to make your hand move to the right, right? The spring is going to oppose the force that you apply into the spring. If you stretch a spring, again, I stretch this spring, I'm applying a force to the right. The spring is going to apply a force to the left, right? But there's more. There's more to it. As you stretch the spring and as you compress the spring, the force of the spring increases. The magnitude of the force of the spring increases. Okay? That's what we call the elastic force. So let me write down, for the case of the elastic force, right? The force of the spring exerts, we call it elastic force. In the case of elastic force of the spring, the force that the spring applies depends on the amount of the displacement that you apply to the spring. Okay? It's given by this formula that you see right in here. There is a negative sign. Okay? X is the displacement from the origin. The object is initially at the origin. And we have this constant factor here. Okay? In the above, K is a constant related to the strength of the spring. Okay? The harder a spring is, the larger is K. By the way, the unit of K is, okay, we can do analysis of the units, right? And we can find out that the unit of the K is going to be Newton per meter, right? If K is Newton per meter, if put Newton per meter here, right? Multiply by meter, you get Newton. The X hat has no unit whatsoever. Okay? So that's the unit of the parameter K. Let's play a little bit more with this force of the string. I need you to have an intuitive vision of how the force of the spring works in the mass, right? So here you go. If I stretch the spring, if I move the mass to the right, the spring is going to resist this motion to the right. Okay? What you see right in here is the vector x, right? The vector x is to the right, and according to my equation, my force must be contrary to the displacement vector. And that's why I have this force to the left. Okay? What's next? Now, suppose I compress the spring. If I compress the spring, the vector displacement is to the left. Because of the equation for the force of the spring has to be in the opposite direction. And the more I displace this spring, the stronger this force becomes, right? So let me just play the movie again for you, okay? I'm gonna play the movie for intermediary forces. Here you go. Like that. The next one, I'm going to stretch this spring even more, right? The vector position of the mass is going to be even longer, right? And here you go, my spring right in here. I'm going to stretch my spring. See that? Because I stretched my spring, now the force that the spring is going to apply on the mass is going to be stronger, right? Compare the length of this vector here with the length of this other vector here, right? You see that? Both vector position and vector force, they increase in length. They're opposite in direction, yes, but they increase in length. So it becomes harder and harder for you to stretch a spring. That's exactly how a spring works, and works in both directions, not just to the right, but to the left as well. Here you go. I'm gonna play the movie for you, right? Playing the movie here. Compress the spring. The mass is gonna go to the left. The position vector of this mass is going to increase. And the force that the spring applies to the mass is going to be contrary to the position vector, and it's going to be stronger, like that. Okay? That's what you have to know. Okay, so the question is, what's going to be the work done by this force that varies in time, okay? That's the question that you have to ask. Okay? So, the question that I pose you, the question that I pose is the following. How do we calculate the work done by the force of the spring? Okay? How do we calculate that? 9:46, very soon we're going to have our break. Okay, and I am going to use my X and Y axis, just like I used before, so you can understand better how you can calculate this type, the work done on this type of situation, right? You go, oh, no, not what I want. I'll have to copy it. Now, you know what? There's an easier way of doing that, doing what I want to do, okay? I don't even need to do that. Okay, I can use this one here. Here you go. Now I have everything that I want. X and Y axis. Instead of X and Y axis, I'm going to put here F, the force, right? And I'm going to come up with the case, illustrate the case of a constant force. Constant force first. And then we're going to get into the case of the spring, the force of the spring, constant force. How does the graph of a constant force looks like, right? As we are displacing the object, displacing that box, right? So it looks like just like that, okay? And let's not forget, it's not just a constant force, but it's the force along the direction of displacement as well. Like that, okay? Let's specify that the component of the force along the displacement. And here is how the force varies. Here how the force is, okay? The force at this position is going to be this value. The force at this position is going to be this value. It doesn't change, right? From the definition, okay? From the definition of work for a constant force, notice that from the definition of work for a constant force, we have the following. right? The work done by a force. And I'm going to use this notation here. Work done by a force, by the x component of the force F, right, is going to be the x component of the force F times delta x. Not this one. Time delta, but fx times delta x, right? Delta x goes is right in here. Delta x is, this one here. I'm gonna put as delta x, and makes sense. Displacement from 0 to delta x. I'm gonna dash this guy right in here. Like that. Okay. So notice that fx times delta x is exactly the area of this rectangle right in here. Make sense? Right? And like that. Okay. The work done, oops, is fx times delta x, which is equal, by the way, to the area of this rectangle. Fx, I will change the font. Calibri, right? Ooh. Calibri, here you go, that's the one. And I gotta subscript that. Subscript, which is equal to the area of this rectangle. Why am I doing that? Because whenever you have a force that changes in time, that changes with position, the work done by that force is also going to be equal to the area under the graph of the force, okay? In the case, constant force, or force of elastic force, it's no longer going to be something like that. The elastic force now is going to be a force that varies with the position of the object, okay? And the work done by this force is going to be this area as well. But this area is going to be calculated differently, okay? It's going to be the summation of each infinitesimal rectangle that you have right in here in this graph, okay? Since this area is the same area of a triangle, we gotta use the equation for the area of the triangle. What's the equation for the area of the triangle? It's going to be this side here, this height, okay, divided by 2, half the area of the rectangle, okay? So let's see here. I'm going to say that let's say that this value is f sub x. Okay. That's going to be f sub x delta x times half. Okay. Area of the triangle. Area of triangle. And the area of a triangle and the area of this triangle is half the area of its respective rectangle. Okay? So here you go. Note that from the definition of constant, we have the following. But this work is also the area under the curve f sub x versus delta x. Okay? F sub x versus delta x. In the case of the elastic force, the area under the curve will be, but this one is also equal, is also the area under the curve. F sub x, which ends up being the area of a rectangle. Oops. Oh my goodness. Rectangle. Okay. In the case of the elastic force, which varies linearly with the position, which varies linearly with the displacement, the area under the curve will be the area of a triangle. Okay? In this specific case, the work done by the spring is by the elastic force will be half the maximum force. Here, I'm going to put it here, the maximum force, right? Instead of f sub x, let's put the maximum force like that, times delta x. Okay. Here the force is 0. Here I call that the force is F maximum. Like that. Did you get the idea? Okay. What time is that? 9:57. Let's take attendance now. And then we go for our break. Today is a lab here. Tomorrow is going to be the last day of the month. Time is flying, huh? We're already at the end of the month of the year. Let's see. Jazzy Castellano, are you there? Just type there in the chat box, Jazzy. Thank you. Gabriel Contreras. I don't see Gabriel here. Yep, I don't see Gabriel here. Nuhamin Wandimu. I don't see Nuhamin either. Okay. Jazz is just by herself. Liliana Cortez. I don't see Liliana here. Next is Molly. Molly is definitely here. Okay. Henry Kim, are you there? Henry is not here either. Laurel Williams. I see Laurel. Thank you, Laurel. Ruth Mandujano. I don't see Ruth. Noemi Martinez. Noemi is not here either. Danae Miller.
Here.
Thank you. Ramon Olivares.
Here.
Thank you, Ramon. Taylor Forn.
Here.
Thank you. Stephanie Ramos. I don't see Stephanie.
Oh, I'm here.
Oh, you're here? Okay. Let me expand here my window so I can see your name. Yeah, okay. Now I see you. It's your name there. Next, Jeremiah. Thank you, Jeremiah. Sean Rosario. Okay, thank you, Sean. Jason Strait.
Here.
Thank you, Jason. Elena Trujillo.
Here.
Next is, thank you, Elena. Jason Valadares. Next is Audrey Aguilar. Thank you, Audrey. Brianna Carrillo. Next is Ali Standard. Thank you, Ali. Alia Zavala. Okay, let's see how many students we have. 10 o'clock. We have 16 students here. We have 16 students there. Okay, cross-check it. So let's go for our break. Break from 10 a.m. to 10:15 a.m. Okay? I see you in 15 minutes. Stop sharing. I'm back here. Let's share the screen now. Okay, so now we're gonna go for our for our lab, right? Insert here, page break. Today's gonna be lab number 5, right? Let's take a look here. Yeah, lab number 5, right here. Newton's second law of motion. Don't forget the report for lab 4 is due now. Let's write it down. Lab number 5. Newton's second law report for lab 4 is due. And by the way, I corrected the report for lab 3. Okay, the PDF file that I uploaded to your group folder. If you have any questions about that, let me know. Let me just okay, so I just before we get into the lab, let me just copy and paste what we have covered so far from the book. Okay, that's what we covered so far. 6.1, work done by constant force, and we did work done by variable force as well. The first and the last section of the chapter. Okay, then we're going to look into the rest as we move along. And get my notes here for lab 5. Okay, Here you go. I got it. Newton's second law of motion. Let me just paste what I copied from there. And then I'm going to report for lab for lab 4. Let's do now. Okay. I corrected the report for lab 3. I will upload the spreadsheet for this lab. Okay, and I want you to understand that there are several ways of verifying Newton's law of motion experimentally. Newton's law of motion experimentally, right? This is the one that we do today. We're going to do today is uses the so-called Atwood machine, okay? And I'm going to come up. I'm going to show you what the Atwood machine looks like. Harbor and LACCD illustration courses. Let's see if it's here. Lab slides. 37. Newton's second law, right in here. Okay, we start with a table. We have a table there in the lab. And wait a minute, before we go into that, I gotta upload your spreadsheets. Raw data. 5. Let's take a look first. Okay, and let's take okay, this one is P06. P06, oh gosh. P06. Ah, P06. Gotta do some corrections here. Oh gosh. Okay, now we have it. Let's take a look at all those files, make sure everything is in good shape here. Okay, good. This one looks good. This one looks good too. This one looks good. This one looks good. This one looks good. This one looks good. 4. This one looks good. This one looks good. And now let me upload those spreadsheets to your folder. Group 1, spreadsheet is available. Group 2, spreadsheet is available. Group 3, spreadsheet is available. Group 4, spreadsheet is available. Group 5, spreadsheet is available. Group 6, spreadsheet is available. Okay, so I'm going to keep on shuffling back and forth between the Word document, the PowerPoint document, and the Excel document, okay? So you can understand how the experiment is done. Okay, so we start with the table. Equipment used, right? Start with the table. Oops. Yeah, here you go. And right here, table support. Next, what do we have next? We're going to have a clamp, a rod clamp. A clamp for the rod, okay? We have those things there at the college. It's a device that we can fit a rod within it, and it has also a clamp. And go right in here. Let's see if we have a clamp out there in the internet, rod clamp there in the internet. Hopefully they have rod clamp. Mount, let's see. Yeah, here you go. See here, we have, that's one type of rod clamp. This one has 2 clamps at 90 degrees. This device right in here, right? What you have here is the rod, and what you have here is another rod. So, oh, here's another rod clamp. Okay, the nail is coming. We have all sorts of rod clamping devices. But the rod clamp that we use also can be attached to the table. Not only it can clamp a rod, but it can also be fit into a table, into our table. Metal rod. Okay, so here you go, metal rod clumped into the rod clamp. Let's attach it to the table. Now, next, frictionless pulley with a clamp. Okay, not completely frictionless, but you know, friction is low enough so we can be neglected. And this pulley also has a clamp in there that's gonna be attached to the rod, to the top of the rod. That's where we go right here. 4. 2 mass hangers. We're going to need 2 mass hangers. And let me attached by a string. Okay, let's put here. Let's put string. 1 meter. Let's see, 3 meter long string. 3 meter long string. Okay. No, it's not 3 meter. It's 2 meters. 2 meter long string. 2 mass hangers attached by the string. And let's take a look here. Here we go. Here are the hangers, the mass hangers, and the string. This is one mass hanger. This is another mass hanger, and they are attached by this string. This string has to be the height of the pulley plus something else. Yeah, 2 meters, 2.5 meters, but must be the right length for it. Okay, and then mass slots. Mass slots. Mass slots. Okay, load both hangers. Mass hangers with these slots. One side we have a total mass M1, and the other side we have a total mass M2. Recall that we use the slotted masses in the first experiment table. And by the way, where M2 will all in this experiment, M2 will always be greater than M1 for the experiment to work. Okay. So if M2 is heavier than M1, it means that your pulley is going to rotate in this direction, right? And this mass is going to lower, and this other mass is going to move upwards. That's how. And by the way, that's what we call the Atwood machine. Okay, the Atwood machine is 2 masses attached by a string and the string passed through a pulley. That's what the Atwood machine is all about. It's this one that you see right in here. And now we can go to our. Okay, so you're going to need to our Excel spreadsheet. You're going to need the 9.8, the value of the acceleration of gravity, all right? And here is my first mass one. My first mass one has 551 grams, whereas my mass two is going to be 581 grams total. Okay, so let's write that down. Next here. Measure M1 and M2 with the provided scale. This scale has a resolution of 0.01 grams, and here you go. Here's the resolution in kilograms. Okay. Now, very important for safety reasons, okay? For safety reasons, to ensure that none of this mass is gonna fall in your foot and it's gonna hurt, okay? Because we are talking about half kilogram here. 2 pounds, right? Half kilogram here, another half kilogram here. We wrap all those masses, all those slotted masses around this mass hanger. And that's what this item is all about. Make sure you wrap the slotted masses in the hanger with masking tape to ensure the masses will not fly away when they impact the floor. Okay, this is a safety issue. Measure the initial height of M2 with a meter stick that has a resolution of 1 millimeter, 0.001 meter. That's what the next slide is all about. Here you go, height of mass 2. this height, you're going to log right in here, data, 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 right? Next, release mass to from rest. Release mass to from rest. And measure how long it takes to reach the floor with a timer. The timer has a resolution of 0.01 seconds. And let's see if we can have a movie here. No, we do not have a movie here, unfortunately. Right? But it's possible to measure the time it takes for mass 2 to go down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 8, 9, 10. Okay, now I'm gonna raise this one by 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's gonna take forever to do that. Okay, that's the first frame. That's the second frame, right? And the third frame is going to be, let's see how, if I can go faster than that. Yeah, here you go. Like that. Let's see this one. Like that. Maybe a little bit more, a little bit higher. Shrink it a little bit. Extend this one. Bring to the front. Yeah. Okay, so here you go. Right? Playing the movie. This is exactly what's going to happen in your experiments. Is if M2 is heavier than M1, see here. One more student coming. Let's see. Okay, I'm gonna do like that. That's better. And now I know how far. Yeah, here you go. And this one's gonna be like that. A little bit more higher, 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 higher. Uh-oh. Like that. Okay. And the last. So like that. Okay, so here you go. Now we have our movie here, right? Here you go. Playing the movie. What we're going to do, we're going to time how long it takes for mass 1 to reach the ground. And it's not just that, but we are going to repeat this experiment 3 times, T1, T2, and T3. Don't forget here is 5 decimal places on kilogram, 5 decimal places on kilogram, 3 decimal places on the meter. And here you're gonna be 2 decimal places, 2 decimal places, 2 decimal places, right? Repeat 1, 2, 3. And then we'll take the average. We're going to take the average right here. We are also going to need the summation of those two masses. Okay, all of those columns here that you see are the data, raw data. Okay, so let's document that in our spreadsheet in our notes. Repeat 2 more. Okay, now here you go. What we have, raw data, M1, M2, T1, T2, and T3. M1, M2, T1, T2, T2, and then we have T3 here. Raw data. Release mass to measure how long it takes to reach the floor with a timer. Resolution. Transfer sum. Oh, very important step here. Now we are going to repeat the experiment, but we are going to repeat this experiment by transferring some of the mass from M2 to M1. Okay, transfer of the sum of the mass from M2 to M1 while maintaining the relation M2 greater than M1 and ensuring that M1 plus M2 remains constant throughout the experiment. Net mass is going to remain constant throughout the experiment. Okay, so here you go. We run it 3 times. We get some of the masses here loaded into there and repeat the experiment. We are keeping M1 plus M2 constant. Okay, as we perform the experiment. The net mass is going to be constant. And that's why I put that column right in here. So you folks can double check that M1 plus M2 is going to be the same right in here. Okay, so repeat it 6 times doing that. Okay, next, calculate T average. That's the T average that we have here for measurement 1 through 6. Okay, 6 times. The average is the average of those 3 here. Average. Okay. Go. Calculate the average. Calculate. What else do we have to do? Okay, we're going to calculate the acceleration of the system using kinematic equation. Okay. This kinematic equation is independent from Newton's second law of motion. So it's not going to affect the legitimacy of the results that we have here. We go from kinematics, we know that y is equal to I naught plus v naught t minus half a t squared, right? Here's a. Negative because the acceleration is downwards. And y naught is the initial height. The final y is going to be 0. The final y, according to this drawing here, right? The axis, let's see, the axis is upwards. Yeah, here you go. Axis is upwards. When M2 reaches the ground, its position is going to be 0. When it starts moving, it's going to be h. Okay. And that, look what we get for the acceleration. We get acceleration 2h divided by t squared. So going back to our spreadsheet, here's the value of the acceleration for all those 6 runs. And I'm going to need the M1 minus M2 as well. Okay, I'm going to need M1, M2 minus M1. Why do I'm going to need M2 minus M1? Well, to find out the net force of our system. Going back here to our free body diagram. Our free body diagram, we have the weight of 1 countering the weight of 2. Because the weight of 1 is countering the weight of 2, the acceleration that this system is going to have is going to be less than g. It's going to be less than 10 meters per second square, okay? Because this force here is countering this other force. And that's going to be my net force of the system. So what do? You're going to plot the net force. Here is supposed to be net. 1, 2, 3. Along the y-axis. And the acceleration along the x-axis. The mass is going to be constant. Okay. We go calculate M. Let me document here before we go forward. We go. Right in. I hate that. Let's see. I just change set numbering value. Yeah. 16. Okay, calculate M1 and to find the net force acting the system. Oh. Okay. And the net force is going to be the difference of the weights. And this net force must be equal to the total mass of the system times its acceleration. MA, F net equal to MA. That's the equation that we end up having. Okay, and I want you to plot that along the y-axis and this one here along the x-axis. Plot according to Newton's second law of motion. Okay, you are going to get M2. You're supposed to get a straight line with a slope that's going to be equal to M2 plus M1. Okay, and then you finish filling up everything. Slope in table 4-5 and check the percentage difference, display the proper units, display the proper number of significant figures, find CL, okay? So make sure you, first step, make sure you download the spreadsheet. At this point in time, you must already have it, right? And plot net force versus the acceleration. I want to check with you if you all of you have the downloaded. And third, download. Jazzy, did you manage to download the spreadsheet? Let's see, Elena, right? Elena, which group are you, Elena?
I'm group number 5. I don't see the spreadsheet. Yeah.
Okay, so let's see, 5. Everybody else in group 5 got the spreadsheet, Jason and the 2 Jasons, right? Did you folks got the spreadsheet, Jason Straight and Jason Valadares?
Yeah, I was able.
Yeah,
Yeah?
I was able to find it too.
Okay, so Elena, can you look again there in the spreadsheet? Maybe it's just a matter of refreshing your browser. Let me go there. Group 5, right in here. Okay, lab number 5. Right in here. See that? That's lab number 5. Why is 2023 here? Yeah, for some reason it's 2023. I do not know why. Let's refresh it. Lab number 5. Yeah, it's still display. Yeah, that's because I modified it in 2023. Okay. So it's right in here. Okay, P06L05G05. Okay, Elena.
Okay.
Okay. There's a bunch of files here. In order to keep it clean, so you don't have too much cluttering, I like to move all those files that we're not using right now to the old file. Sometimes it's just the cluttering that, and let's see, I correct lab 3, right? Okay, and I need to know. Okay, don't forget to keep I need to know which one I'm going to correct. Okay, group 5, I want to know if I have to correct this one or this one. Okay. Can you tell me which one I'll have to correct? That's the lab number 4.
I guess the top one.
The top one? Okay. Can you please rename it? Okay, P06L04G05.
Okay.
Okay, just like it. Okay, so I'm going to move this one elsewhere, okay? In case
Okay.
you're going to, since I'll be correcting this one. And that goes for the other students too, okay? So here you go. 02, 02, 03, right? And 03. 04 is there. So that's the one I'm going to correct, okay, group 1? Group 1 looks like we have just one student there, right? Lonely student. Let's see. Yeah, Jazzy, you are by yourself, right, Jazzy? Your group members didn't show up today. Let's clean the other ones. Here you go. Group 2 makes things easier for me, okay? Let's see, you're supposed to have 4, right? Okay, I need you folks to tell me which one do you want me to correct? This one here or this one here? I presume that you want me to correct this one here, right?
Yes.
Okay, so let me move this away. And I'm gonna come up with a old files, okay? And I'm gonna put everything right in here. And then if you want to create a lab for, let's see, this one goes to old files as well. And I will correct this one right here. Group 3, let's see, group 3. 2, 3, I've already corrected, put it here. And you want me to correct this file here, right? Group number 3. Let me call group number 3. Group number 3 is Noemi. Are you there? Noemi is not here, right? Yeah. Ruth is not here, but Danae is here, right?
Yeah, I'm here, but Ramon sent you a message in the chat. He's also in group 3.
He's also in group. Oh, okay, Ramon, let's see. Haven't submitted. Can I do it after class? Okay, well, okay, make sure you upload it before the end of the day today, okay? Before the end of today. So I'm going to, let's leave it for now. Group number 4, let's see. 2, 2, 2, 3, 3, 3, right? Place it right in here. Okay, 4. And I'm gonna correct this one here. And group 5, did I went through group 5 already? I think I did. And group 6. Okay, 2, 2, 2, 3, 3, 3, 3, 4. Okay, group 6, I understand that you want me to correct this file here, right? 1145, the latest one. And I'm going to move it elsewhere. And so going back to my roster. Good. Next one. Gabrielle is not here. Nohamin is not here. Lillian is not here. Let's see. Molly, you download the spreadsheet, Molly?
Yes.
Okay, thank you. Henry is not here. Laurel, did you upload the spreadsheet, Laurel? What happened to Laurel? He was here. Okay, looks like Laurel left. Okay, let's put it here. I'm gonna put a star. His name, Bruce is not here. Noemi is not here. Danae is here. Hello, Danae. Did you download their spreadsheet?
Yeah, I did.
Okay, good. Next is Ramon. Did you download their spreadsheet, Ramon?
Yes.
Next is Taylor. Did you download their spreadsheet?
Yes.
Next is Stephanie Ramos. Did you download their spreadsheet, Stephanie?
Yes.
Okay, thank you, Jeremiah. Same question. Yes, thank you, Sean.
Yeah.
Okay, thank you, Jason Straight.
Yep.
Okay, Elena. You download their
Yeah,
spreadsheet?
I was able to download it.
Okay, thank you. Jason Valadares.
I got it.
Okay, thank you. Audrey.
Yeah, I was able to.
Okay, thank you. Brianna. Yes, okay. One more. Ali Standard. Hello, Ali. Okay, I'm gonna put a star here at Ali. Alia Zavala, did you download their spreadsheet? Yeah, okay, good. So yeah, good. So next step here is to plot the graph. Plot graph, right? So let's work on that. Start working on your graph. I'll give you a few minutes to do that. Okay.
Sir,
Yes.
what are we supposed to, which parts of the graph are we, I mean, the table are we supposed to graph again?
Okay, so here you go. It's written there in the spreadsheet, right in here. See that? Plot Fnet in the y-axis and A in the x-axis. So you highlight it here. You highlight this one here.
Okay, thank you.
Okay.
My bad.
If you have plotted the graph, let me know, please. On the graph, is the net value the slope? Now, on the graph, is the F net value the slope? No. Let's see. When I plot it, the graph here for you. F net goes in the y-axis, right? Okay, here you go. Y and x-axis. Insert. Okay, I'm getting this odd graph, okay? So it seems to me, my goodness. Let's see if we get, let's get a trend line here. Yeah, okay. Yeah, we have, it looks like we have two outliers, this one and this one. Looks like those two are outliers. And I want to find out what is M1 plus M2. Yeah, even though we have those two outliers, we still got a good slope. Okay. Here you go, Molly. The slope is this value right here. Okay. And that's the one that you have to log back in here. And let's copy the 8671 point 8671. And I'm getting, 23% because of those outliers there. If I remove one of them, most likely you're gonna get, I want to remove this one. 2 minus 1. Let me put this guy here in, so I can read the numbers better. Number 1, 2, 3, 4. Yeah. Table 4-4. Okay, let's go there. 4-4 is, okay, here you go. Remember, that's the regression equation, right? Those labs always follow the same script. What goes here in this table is the regression equation. The regression equation you write down right in here, okay, Molly? That's what you write down here. You already have the regression equation on your graph. And let's get this one here, number. The problem of having it in a scientific format is that you do not know exactly what those values are, right? 0.0776, so it looks like the outlier is this one right in here. That all looks like. Now looking over, I think no. The outlier is actually those two here, or even maybe this one. Well, we have to experiment to find out. Okay, but let's leave it this way. We are not very off. If you're doing an actual experiment, I was going to ask you to repeat those three. Looks like those three are the outliers. Let's see. I'm going to cut down, remove them. Those three outliers. Looks like those are the three. Yeah, here you go. You're getting still 1.2. 1.2 is still a high value because this. If I put 1.2 here, oh, it's better than the other one. Only 5%. Yeah. See, by removing the outliers, we get a better slope. Right? Now let's put back the outlier, some of the outliers one by one. See, got worse. 1.45 got worse, terribly worse. Let's remove this outlier. Let's see. Oops. Let's see if I can get no. What about that? I'll plot it, insert it. Wow. Yeah, okay. I think I'm gonna get a better slope now. Let's see. No, 0.8375. Yeah, 8375 is gonna be close to 20%. So it looks like Microsoft Word is not doing what I wanted to do. I'm doing everything right here. I do not know why it's not highlighting. Okay. Strange. Let's see. Let's remove this one. Well, you don't have to worry about finding, removing the outliers. Just plot everything in there. I just want to find out what. So the problem seems to be all those 3 points. That the problem seems to be. Let's plot this one here and see if we get a better result. Nope, we don't get a better result. Let's see. 85, yeah, 20%. Okay, so can play it a little bit and let's see. Let's see how you are doing there. Plot the graph. Jazzy, you manage to plot the graph? Working on it? Okay. So let's wait a little bit longer. Maybe everybody else is Montreal, Gabriele, Montreal. Plot the graph. Don't forget get R square, get R square. Regression equation. Right? I want you to get the regression equation. Slope. Record the slope in the last table. What else? Check percentage difference, right? Check percentage difference for the slope. And then you do everything else that you're supposed to do, units. Sig fig, right? And then you do the CL. I was doing the graph and it didn't look like the one you did. Can you go over it again? Okay, let's see. Your group number 5 or 6? 6, right? Audrey. Let's look at your group. Well, it's not gonna look like mine, okay? Because those are different data sets. Okay, but let's take a look right in here. Group number 6. I was doing group number 7. Another set of. Okay, so I'm gonna plot FNet and A. Insert chart. Okay, much better than the other one. You have much better data than the other one. Okay, does it look like that, Audrey? Does your graph look like that? Okay, good. So yeah, it looked different from the other one because the other one has different data, right? Now here you go, add trend line, display equation, and okay. See the slope here? It looks like it's a very good slope, 1.1286. I'm gonna log it right in here. Oh, no. Let's do it again. It doesn't let me copy it. Yeah, it doesn't look like it let me copy. Let me try to paste again. Okay, it let me paste. Do you see the percentage difference here? Very small, 0.12%. Okay, Audrey? So let me take it out. I will erase this one as well. Eleven, 12 already. Huh? Hey, we need to go into a break, right? Okay, let's go for a break. And then we reconvene at 11:30. Break. Let's put here 11:15. Let's wait another 3 minutes. Two minutes, huh? In this meantime, let's see how you're doing there. We'll use those 2 minutes and then we'll go for our break. Roster right in here. Molly, did you plot the graph, Molly?
Yes.
Okay. You got the R square and the regression equation?
Yes.
Yes, okay. Did you log the slope there in the last table?
Yes.
How much percent did you get? How much percentage difference you got?
Let's see. 14.96.
14, okay, 0.9, yeah. Kind of high, but that's okay. You don't have to worry about that. Let's go, let's see, 11:14, this Laurel. Laurel was here, but he left, right? Okay. Ruth is not here, Noemi is not here. Danae, did you plot the graph?
Yes.
Okay, good. Did you get the R square?
Yes.
Okay, the regression equation?
Yes.
Okay. And did you get the slope? If you got the regression equation, you got the slope too, right?
Yeah.
Okay, what's the percentage difference you're getting?
I have to plug it all in though. I haven't typed everything in. I'm just looking at my graph right now.
Plug there, so I'm gonna put here you're working on that.
Yep.
And now it's 11:15. Let's go for our break. I'm going to stop sharing. I am back here. The last one I talked to was Danae. Ramon. Ramon had a question, right? He was asking about the outliers. Is that right, Ramon?
Yeah,
So your group number 3, do you have an outlier there in your graph?
I believe so.
You believe so? Let's take a look there. Group number 3. That's one. Okay, did you plot FNet and A?
Yeah.
Yeah, you did, right? So let's take a look. Oh, yeah, it's similar to that graph that I had. Yeah, looks so ugly, right? Yeah, well, keep them all in the graph, okay? Go ahead, add the trend line, keep the R square. And we're getting, oops.
My percentage difference is only 1.7.
Let's see what's the percentage difference. Let me first trend line linear. What's going on here? Let me see. Let me redo it. Okay. Let me display equation. All right. Let's take a look at the slope. 1.1572 doesn't look like high to me, despite the outliers. 1.1572, right? What's going to be? Did you get 1.7% for the percentage
Yeah.
difference? Okay,
Yeah.
so that's low. That's a low value. You don't have to remove any outliers from there. Okay,
Okay, thank you.
just plot whatever you have. Just leave this way here, and that is Ramon. See. Yeah, so you plot your graph, right, Ramon? You got the R square. Is that right?
Yeah.
And the regression equation. You got the slope
Yeah.
as well, right? And you got a 1.7% difference, right?
Yeah.
Okay, that's good. So next in line here is Taylor. Did you plot your graph, Taylor?
Yeah.
Okay. You get your R square?
Yes.
You get your regression equation?
Yes.
Okay, did you fill the slope into the last table?
Yeah.
What the percentage difference you got?
I got 18%.
18%. So let's see, you're group number 4, right?
Yeah.
Let me get that. This experiment is a little bit difficult to perform. That's why we're getting some high percentage differences, right? There you go. Okay. So it looks like this one is the outlier. That of this one here. That we never know until we get our regression equation. So yeah, it looks like it's 18%. Let's see, 937.937. Yeah, 18%, just like I got. That's okay. Okay. And you got hit 18%. Keep the outlier there. Don't worry, unless you want to play on your own, just like I was doing before. I was playing with the data points. Let's see. Like I said, this one seems to be the outlier. How do I know it's the outlier? First, this point is outside the straight line of the other points. That's for sure. But then there is one more thing too. This one is the outlier because this point by itself is bringing down the slope of the curve. Okay, we want a higher slope than that. We want a slope that 1.1, 1.2. Okay, and because this point is downwards, it is bringing the slope down. Okay, that's how we identify the outliers. Now let me put the format cell here, number 1, 2, 3, 4. Everything. Now let's see which one is going to be the outlier. 0.26, 0.47, 0.2. Yeah, that's the outlier. That's the outlier here. Now I'm going to plot without the outlier. Okay, and let's see if we get a better result or not. No, without the outlier. And note, see that when those guys performed the experiment, that's bad practice, okay, what they did here. They have this huge gap here between those 2 points, okay? They should have chosen masses that would fill up this big gap. So it looks like they made a huge jump from one mass to another one, and we ended up with this huge gap. Okay, that's something else that you gotta keep in mind whenever you're performing an experiment. Now let's get the trend line there. Oh, see that? I removed the outlier. I got closer to the actual value. You know, 7% better. It looks like it's 7% better. Let's see. It looks like that instead of 18%, it looks like you're gonna get 11% now. Let's see. 1.005, 1.005, 12%. I was close, right? I said 11%, but it ended up being 12% just by removing the outlier, okay? The other outlier looks like this one here is another outlier. It's a minor outlier because it's making, again, the slope of the curve goes down, okay? So let's remove this one as well to see if we get even closer. Ah, strange. Okay, so this one. Point 029, 0.278. 0.029, 0.278. That's the other outlier. Okay. The first outlier was this one here. Let's see. First outlier. Let me just yeah. 0.0298, 0.27. Yeah. Let me highlight this one so I don't forget. The other one was, which one was? I believe it was this one, right? 26164708. Yeah, the other outlier was this one here. Now let's see if we get 1, 2, 3, 4. But don't forget, as we remove the outliers, we also end up removing the number of data points, right? So you gotta be careful about that, about removing outliers. You may impact the result of your graph negative. Okay, yeah, see that? It is going closer and closer to the 2% closer, apparently, 1.0231. But it's not much of an increase, okay? It's not much of an increase, 1.0231, 1.0231, 10%. I got only 2% better by removing. When you get such a small variation, right, in the percentage difference, it's not recommended to remove the outlier. Okay? Yeah. Okay, so let's go for a next student here. Stephanie Ramos. Did you
Yes.
plot your graph, Stephanie?
Yes. We almost got the same thing.
I didn't understand. I'm sorry.
Oh yeah, I did plot the graph.
You did? Okay, good. So yes, did you get the R square?
The R square is, hold on, where is
You don't have to tell.
0.984?
Okay. Yeah, seems right. What about the regression equation? Did you get the regression equation?
Not yet.
Not yet? Do you know
Yeah.
how to get the regression equation?
No.
You don't know. Okay, so here, group
Sorry.
number 4. Let's get group number 4. Okay, I was doing that for group number 4, right? Gotta have to learn how to get the regression equation, okay? So here you go, I gotta plot the graph, right? Fnet and A. Insert chart. Okay, that's the graph you get. Click one of the data points, right click, add trend line. When you add the trend line, you're going to have the option to display the equation chart and display the regression equation. Display the regression equation chart and display the R square value on chart. Okay? That's how you do
Oh,
it.
okay, got it.
Right?
Oh, so it's just a 0 point, this thing up here?
The R square is
Oh, okay, I see.
0.9144. Regression equation is this one right here at the top.
Okay.
That's the regression equation. Okay, now you're going to be working on that. You got working on the regression equation, right? But did you plug in the slope there in your table?
Yeah, the slope 0.937.
Yeah, and what was the percentage difference?
Percentage difference 18%.
80%. Okay, good. Next, Jeremiah Reyes. Your turn, Jeremiah. Did you plot the graph? Yes, okay, good. Did you get your R square? Yes, good. Did you get the regression equation? Yes, too. Let's see the slope. Did you type the slope there in the cell of the last table? Should work on the slope. Okay. And the percentage difference. Okay, that's good. Next is Sean. Hi, Sean. Are you there? Okay, did you plot the graph? I presume you did, right? Okay, what about the R square? Did you get the R square? Yeah, okay, good. The equation, the regression equation. Yes, okay. The slope, did you log the slope there in the cell in the last table? What's 0.937? How is the slope, right? Is the slope value? But what's the percentage difference you're getting? 18%, just like everybody else. Okay. Now let's go to group number 5. Jason, did you plot your graph, Jason?
Yes, I did.
Okay, did you get the R square?
Yes, I did.
Okay, regression equation?
Yes.
Okay, good. The slope, did you log the slope in the last table?
Mm-hmm.
Okay, what's the percentage difference you're getting?
I got 9.73%.
Okay, 70, that's good. Opa, not 93.
9.73.
73. 9.73. Here you go. Thank you. Now, did you start work on the units as well? Okay, start work on the units, okay? So let's see. Jeremiah, you want to say something? I have gotten. Okay, what's the percentage difference you're getting? 18. Okay, good. So next one, Elena, are you there?
Yes.
You plot your graph, Elena?
I did.
Okay, you get your R square.
Yes.
Okay, and the regression equation as well.
Yes.
Okay, the slope, you gotta did you put the slope there in the last table?
Yeah. So my slope was 1.24,
Okay,
and then I got 9.38%.
9.13, you said?
9.38.
38 for the percentage difference, which is different
Yeah.
from JSON, right? Let's see. There's a difference here. Well, let's see what's the problem. Let's see, group number 5. Let's get a small difference. Group number 5 here. Net force, acceleration, insert. Okay, wow, that's yeah, see, definitely this one here is a outlier. Now let's see, 1.244. Now looking over, I don't think this one is the outlier. I think now that this one is the outlier. Okay, 1.244. 1.244. 9.73. Okay, so it looks like the other student is correct. Let's see. Roster 9.73. Check again your percentage difference, okay, Elena? And you should get the same value as Jason got.
Okay.
Okay. So Jason Valadares, you plot your graph?
Yeah.
Okay. Graph R square.
Yeah, I got it.
Okay. A regression equation.
Yeah.
Okay. The slope.
Yes.
Okay. What's the value of your slope, please?
The slope is that I got is 1.2444.
244. Okay. Which is the same I got, right? Let's see. 1.244. Yeah. And then you should get 9.73, right? Just like the other Jason.
Yeah.
Right? Okay.
Mhm.
Thank you. Now group number 6. Audrey, did you plot your graph? I'm still working on that. I had some issues. Okay, still working. Okay, so I'll get back to you later. Brianna, did you plot your graph? Yes, all I need to do is this. Okay, good. Yes, yes. And what's the value of your slope, please? Since you plot your regression equation, you should have the numerical value of the slope. Okay, and what about the slope? Okay, so let's move on to the next one, and then I'll get back to you. Let's see, Ali Standard. Are you there, Ali? Looks like Ali left, huh? Yeah. Yeah, left. Next is Alia Zavala. Slope, okay, let's see. R square 1.1286. 1.1286. Yeah, and you get a very small percentage difference. That's good. Okay. So let's cycle back to the top. Jazzy, did you plot your graph? Last time I talked to Jazzy, she was working on the plot of the graph. Hello, Jazzy, are you there? Okay, I'm gonna put a star here next to her name. Let's see. And let's see the other one. Danae, did you finish? Did you get your percentage difference, Danae?
Yes, I did.
Okay, and what's the value of her slope first? Let's see.
My slope was 1.1572.
1.15. Okay, and what percentage difference do you get?
It was 1.7.
1.7, just like
Just like
Ramon.
Ramon.
Yeah, just like Ramon. Okay, good. Are you working on the units already?
Oh yeah, I am.
Okay, so put a W here for working. Let's see, anybody else? Brianna. Okay. Audrey was working on her graph.
Professor.
Yeah.
And now I got the percentage 9.73.
Okay, who is that?
Elena.
Okay,
Yeah.
9.73. Okay, did you find out what was the problem?
Yeah, I guess I didn't press enter.
You
And
didn't
then
press
I
enter.
find
Okay.
if I
And,
never
and
corrected it though.
okay, you got the same slope as Jason, right?
Yeah.
Okay, that's good. Okay, 11:52. We still have 8 minutes to go. Start working on the unit, right? Brianna. Are you there, Brianna? I can't hear from Brianna. Let's put this.
Faja?
Yeah, is that Brianna?
What you got in mind for lunch?
Lunch?
Yeah.
Looks, someone left that mic on. Slope 1.13, right? 1.13. And what's the percentage difference for that, Brianna? Point 123. Okay, 0.123, just like the other student, right? Just like Elia. She got 1.1286, which is when you round that up, you get a 1.13, right? Which results in the same percentage difference. Okay, and Jazzy, going back to Jazzy. Hello, Jazzy, are you there? Okay, let's skip here to Molly. Molly, did you work on the units?
Yes.
Okay, so you did the units, sig figs as well?
Yeah, I think I'm set for
Okay.
those. For the acceleration and the FNet, is the acceleration 4 decimal places and then the FNet is also 4?
Let's see, you're talking about the sig figs, right? Let's go there.
Table
Group number 2, right? Let me get your spreadsheet of your group. Okay. Okay, so here you go. The significant figures of the you're asking the significant figures of the acceleration, right, Molly?
Yes, and the FNet.
Okay, let's go for the acceleration first, right? The number of significant figures of the acceleration is going to depend on the number of significant figures of the height and the number of significant figures of t, average. Okay? So first you gotta get the significant figures here, right? Did you get the right significant figures for the h?
Yes, I did
Okay.
3 decimal places.
Three decimal places, right? So let's go here. Number 1, 2, 3. Okay. So you have we have 4 significant figures for each. Okay. Now you have to worry about the number of significant figures for T average. But before you get the number of significant figures for the T average, first you have to get the number of significant figures for T1, T2, and T3, right? Did you do that?
Yes.
Okay, so it's 2 decimal places for all of them. 1, 2, because the resolution is 0.01. Here you go. And now look what happened here. When I sum T1 with T2 and T3, we get a number more than 10, right? Sum those 3 divided by 3, you get the average. When you sum, you end up with a number equal to 12, whatever. So from 3 significant figures, you increase your significant figures to 4. So this T average here should have 4 significant figures. 4 significant figures should be 3 decimal places in this format. Okay? Got it? Now you can find out the number of significant figures of the acceleration. Okay, you have to do all of that before getting to the number of significant figures of the acceleration. You have 4 significant figures here. You have 4 significant figures here. How many significant figures are going to have here?
4.
4. Yeah. So for math, I think you're going to need 4 decimal places. 1, 2, 3, 4. Let's see. Yeah. 4 decimal places, 4 significant figures, right? And then you repeat all of that for the rest. Okay? You already have 4 significant figures here. Here you're going to have 4 as well because 5, 10 is going to be 15. Okay? All the way up here is going to be 4 significant figures. Okay? All of those is going to be 4 significant figures. Number 1, 2, 3. And then the last one is 4 as well. You have 4, 4, 4 here, but when you sum them, it does not exceed 100. So you keep 2 decimal places, right? Yeah, you keep 2 decimal places instead of 4 decimal places. 2 decimal places results in 4 significant figures. And now you can get the number of significant figures for the rest of the acceleration, okay? That's how you do the 11:58. Let's see. Well, do you need any help? We are almost running out of time here. Okay. So if you do not have any questions, we can stop now. And we will meet again on Monday. Let's do that. Okay, so I see you on Monday.
Thank you, Professor.
Welcome. Stop sharing and stop. Stop recording.